Okay, let's start. Before we now begin with the finite element method, which will keep our attention for a long time, I will make a few remarks still to the finite difference approach. Maybe we will come back to it a little bit later, but only after we really have dealt with the finite element method extensively. So the one remark concerns a little bit of a refined argument compared to what we have done already. So let's call this a refinement of the order of convergence estimate. Always in the framework we have discussed last time, in particular meaning that we always assume that we are dealing with discretizations where the discretization matrix is inverse monotone. And we have seen requirements which are sufficient for that. And you remember the basic thing was to also in this, under this assumptions also to come to stability. One decisive step was to look at grid functions WH such that AH/WH is greater or equal in the pointwise sense than the vector 1. On the basis of this, having such a function, we have seen that basically on the basis of the infinity norm of this function, we could build up a stability estimate, of course, in the situation where we have a uniform bound on this L infinity norm. There's a little bit more in this approach. We can do the estimate a little bit more refined. And this is then also the basis why we can do a little bit better in situation where we up till now thought, for example, in the situation on general domains with then non-equidistant stencils, we up to now we said, okay, if this is necessary, then we only have first order of convergence because near to the boundary we have a stencil which has only first order of convergence. This does not need to be the real truth, as we will see. So what can we do in such a situation a little bit differently to what we had till now? So if we look at the grid function u, so this is just the evaluation of the exact solution. If we plug it in, then we get, so to speak, the normal right-hand side, and we get something which I now call QH hat, which is just the consistency error. That's just the definition of the consistency error. We have our consistency error estimate. We also, so to speak, the further assumption is that we know the consistency error in the discrete L infinity norm behaves like a constant 2 times h to some power of alpha. That was always the general situation we had. So now let's modify our argument a little bit by looking at a function w tilde, where we just take this w but scale it, let's call this C1, as I had it also C1 here, scale it with this factor here. So what does that mean? Then just by plugging it in, if I again define with EH now the error, so EH should be UH, the grid function we are computing, which are approximation minus the grid function U, the exact solution. But this is now a grid function, it's not a norm. We look at the full error function, not at the norm of the error function at the moment. So what do we know? We know by this definition and just by this estimate here we have on the consistency error that if I compare AH applied to E epsilon, this is error function, and I compare AH compared to the applied to the W tilde, I have less or equal. Just put in all these inequalities, then you see this immediately. But by inverse monotonicity, this means that we have an estimate, which is now not a norm estimate, but a pointwise estimate at each grid point. A pointwise estimate says that the error grid function can be estimated by C1 H alpha times omega H. And analogously, we can do the same estimate from below, saying that we get then minus C1 H alpha omega H less or equal to EH, or put it together, we have, and this vector, this is now a vector still, meant to be the vector composed of the moduli of the components, can be estimated by C1 H alpha H to the alpha omega H. So now, of course, I can go on with this estimate and say, of course, I can estimate this now from above here with the, say, infinity norm of this vector. And if this is, again, stability bounded by some, let's call this, I think, C bar, then we are in the L infinity norm estimate as we are used to. But the step in between, this says a little bit more. This is now a pointwise estimate here. And of course, the shape of this function W now enters into this estimate. And if you remember the functions W we have constructed last time, this were these parabolas, which were, in particular, they were zero at the boundary. That means we have a certain factor, which is not something different, just the power of H, which weights the error differently on different parts of the domain. So if we have here a function WH coming from a function W, which is zero at the boundary, this reflects the fact we have Dirichlet data. At the Dirichlet boundary, our solution is exact by definition, and this is then reflected in this pointwise estimate. Whereas if we now go to the infinity norm, then we lose this pointwise effect. Kann ich weitermachen? Okay, so, and this is the key that in this situation we have discussed. So I don't want to formalize that, because formalizing it requires a lot of detailed considerations for which I don't have the time. So the situation is we have an arbitrary domain, and I put this here in parentheses because it cannot be totally arbitrary. You see, for example, if I make this, I put it here together, then, and you see the grid points here, then I will lose the connectivity of the grid set. I will lose the irreducibility of the discrete equations of the matrix, and also this weakened form of irreducibility if I have a part which has nothing to do with the other. So there are some assumptions which I'm not going to specify now. But the problem which we discussed already is if I in the interior at a point far away from the boundary, in the sense that all the neighbors of the 5-point stencil are in the domain, so we are still in the model problem. So if I in the interior, I have this stencil, and I know everything about this stencil. I know its consistency error H square. But if I'm close to the boundary, for example, at this point here, okay, so I come to this stencil then, is also a 5-point stencil, but it's not equidistant anymore. I have to shift, I have to take those points of the boundary which are on the x and which are the projections, the x and y direction correspondingly. So here and here the Dirichlet data will go in, but now I have a stencil which is not equidistant, and this has the consequence that here I lose one order in consistency. So the problem is what is the influence of that? And if we do it up to now with norm estimates, we estimate an infinity norm, so we always have to look at the worst case, and so the worst case would determine the order of convergence, saying the order of convergence is only 1. Which is of course not wrong, but the question is it an optimal result? And the point really is here, with these a little bit refined estimates, we can see that, and I do it very, very informal, that the order of convergence under all these assumptions we have done, C4 and so on, all what we need to do all these estimates, is here still 2. How can we see this? Okay, so let's have a look. What do? We have again our consistency error. So this is a sketch, very brief sketch of the proof. You have our consistency error, the thing which I denoted by QH hat, and we subdivide this in 2 parts. QH hat 1 and QH hat 2. The 1 is the one which comes from these grid points away from the boundary. And the 2 is so this is something which is non-zero here in the interior of the domain and 0 in a vicinity of the boundary. And this is just the opposite. This is the consistency error which comes from this type of stencils. And what do we know about the estimates? So this is away from the boundary. And this is close to the boundary. Okay, what do we know? The one is the one we have estimated all the time. Here we can just look at the infinity estimate and we see there's some constant. That was this with the 4th derivative and so on. There's some constant times h squared. And for the other one, it doesn't look as good as we know. The other one, I give the pointwise estimate first, can be estimated only by h over 3. And now these fractions which play a role here, and maybe I indicate them, I indicate the notation. If I have such a, let's say, such a stencil, then so I don't have here the distances 1 times h, but something times h. And this something I call here, so this is a number between 0 and 1, and I just call it according to the geographic, not to the geographic, a little bit to the geographic, no, it's not to the geographic direction. This is SR, so this is German notation, S rechts. This is SL, this is SO, and this is SU, SU. Oben, unten, links, rechts. This is the notation which I use for these lengths. So these are numbers between 0 and 1. And these numbers appear here, and I get estimates, basically SR square plus SL square over SR plus SL. And here I have the 3rd derivative only to use in the x direction. And I have here a similar thing as now just the other way. And you have the third derivative in the y direction. So, and unfortunately I only have the h here. Okay, so let's see what we can do with that. Okay, this subdivision, as we know, we have an inverse monotone matrix. We have a regular matrix in particular. We can solve any set of equations for any right-hand side. So we take these consistency errors and, so to speak, compute error contributions corresponding to these parts of the consistency error. So we subdivide the error into two parts, 1 and 2. Again, the vector as before. By definition, the part 1 is the part 1 which corresponds to the interior part of the consistency error, and the part 2 is the part which corresponds to the boundary part. So this guy here is okay. This is, here we have an h square, we preserve this h square and so on because of stability. This is the critical thing here. Why is there some hope? Let's think a little bit about that. So what is behind this AH? It's a discretization of a diffusion process. And what do we have here? We have a distributed source. This distributed source has the size h. This is too big. But the source is only distributed near to the boundary. So let's think of a sort of a diffusion of the error which occurs here. This is nothing but a discretized diffusion here. So we might have the hope that this will produce in the interior of the domain something which is then smaller by this diffusion process. So we have a source. You can think of a diffusion process. You have a source which is big, but it's located. Now diffusion starts. So the mass or whatever will distribute and the maximum will decrease. And of course, what we want to see is that we go down now from h to h square. Let's see whether this can work. And I will not do all the computations, but just have a look at it. So what kind of arguments what we need is, we have to distinguish, so we discussed this thing here. And we have to distinguish between first a point which is far from the boundary, or away from the boundary, I have called this. Okay, away from the boundary, okay, sorry, I have to. We need now this auxiliary function we have dealt with, this omega h. So we do the same thing. So we have again omega h and omega 1h, omega 2h. And so the omega 2h we have not to look at. This is a constant times 1. And the constant is exactly a constant. What is the constant? This is 2/3. This is tailored. This is tailored that in the end it works. At the moment it's not so obvious why this really works, but let's just do it. So again, these quantities from the estimate of the consistency error appears, but now with a much larger power, h3, and then I have something which appears with, so you see this has something to do with, where is it, with this type of estimate, and this has something to do with this type of estimate, which I have not written down explicitly. There we had the fourth order derivatives. And here we take then the h to the 4. Okay. Whether this k makes sense or not, this we do not yet know, but we can investigate what this function w does. And let's see how this reacts in conjunction with our difference operator, our AH. So if we are far away from the boundary, then there are no Dirichlet data which influence, which reduce the stencil. That means we have all values in the stencil. That means all elements in this row add up to, all components in the row add up to 0. We have the minus 4 and 4, we have the 4 and 4 minus 1s. That means if we, this was now a little bit too early here, if we now look at a node which is far away, far from the boundary, we just see that AH, WH, this has nothing to do with the choice of the k, is 0. This just says the sum in each in this corresponding row is of the components is 0. And now we look at the points, so of course I here. And now we have to look at the points which are close to the boundary. Now, in principle, one has to go through all the various possibilities which are possible. You see here, this is a situation with 2 points. We could also have 3. And if we do not restrict, so 4, I think we can exclude by saying this region should not be too bad. But we have in principle, similar to what we have seen already in the rectangular case, in principle all the 3 possibilities can appear. 1 on the boundary, 2, 3 compared to the stencil. And in principle we have to go through all these cases, and I will do only one example. So what does that mean? Wait a second, what did I do? Yeah, what do we, yeah, this is what we have, and what we have in this case. In this case, in general, we have let me write it in this form. We have something like yeah, not the 0, but what goes, so to speak, in the boundary condition. And this can be between 1 and 3, and if it's too strange, the region, maybe even all the 4 neighboring points go into the boundary condition. So we have here something like minus k, and here we have then the entries. And here, so let's say, j from the neighboring set of this index I. Example. Let's say xy is our point we are looking at, and xy minus suh, the left boundary, the boundary point below is the one which is in the neighbor point below is in the boundary set. So we have then to look what now this means, what these quantities mean. So now we have to really to deal with these S values, which I'm not going to do in detail. And what comes out, and when we skip this computation, what comes out, we can estimate this from below. So there's some computation in between by exactly what we have defined as QH hat second part. And this is by definition, that's the way we have defined the second part of the error. This quantity here. And we can take here the modulus. Why can we take the modulus? Because the Q is a non-negative function. Okay. So, and this as a consequence now again, you see, we can again apply inverse monotonicity, and this tells us that at the end, this critical part here can be estimated by this WH2. And this WH2, where was it? That has even only third powers. So this, so to speak, diffusion of the small banded error means that in total we can, in this limit process, stationary process, which in the end we are seeing, means that we only have here a third order of convergence in this part, in this part which had made us headaches. Of course, the other part, this is no problem. This is, so to speak, our old estimate, and together then we have really that we have CH square. It's a little bit astonishing, and I also had to really convince me that this really makes sense, because it's really astonishing that this error, so to speak, induced by this small banded consistency error, which is way too large, which is the order of h, then in the end produces such a small contribution here. But yeah, I think if you what helped me is to see this analog with the diffusion process, because actually that's what we are doing. We're discretizing a stationary diffusion process. So this tells us that there's a little bit more in this method. Not only L infinity estimates, but also doing, if we really do these pointwise estimates as far as we can do them, by means of this inverse monotonicity, we get more information, we get different information at different points in the domain, close to the boundary, far away from the boundary. Okay, maybe another remark. I've probably lost already much too much time for that. Another remark for the pure Neumann case. We discussed this already, the pure Neumann case, and we have seen, obviously, in the pure Neumann case, we cannot have a unique solution, because there are only derivatives. And of course, if we have a solution, if we add a constant, then again we have a solution. We can look at this a little bit more closely. So let's have a look at this here, pure Neumann case. Again, what do I mean by that? Again, the model problem. And now, instead of the Dirichlet boundary condition, the normal derivative of u is prescribed to be given by g. What does that mean? We have a process which has a distributed source f, which has a flux. So what is this? This is the outer normal n, but the flux in this normalization is minus gradient of u. So this here is the flux into the interior. Okay. And we say this process has a stationary solution. What does your physical imagination say? Do you think this is always possible for every choice of f and g? A distributed source and an influx described by g. Always a solution or not always? Take one of the choices. Not always. Why? Pardon? I don't understand you. We have a distributed source and we have an influx. Is this possible to have a stationary solution in such a situation? Under which requirements? Is it always possible? Yeah.
I think it's not possible because you pump energy into the system. So if you have a source and an influx,
okay, yeah.
you have very high temperature, for example. And
okay, that does. It would say what doesn't seem to be possible is that f is non-positive, that we really have a source. If I say source, I always say source or sink, and whether we have a source or sink, also depending on the point x, is regulated by the sign of the f. So this combined with a positive g does not seem to be possible. But is a positive f with a negative g maybe possible? Seems so. Okay, so let's do simple computation. So what is this? I integrate the equation. So what do we have here? We have, that is where the equation comes from, the divergence of the gradient of u. What is this? So we, so to speak, go back in our development of the equation. Now what can I write for this term here now? Pardon? Yeah, but that does not help me too much. This is a volume integral over divergence, and this is also then what? How do we have derived this equation?
over the area.
I write what you say. Let's say d sigma, because it's a surface integral. And what is this last quantity now? What is this? What has this to do with this one? No vector calculus? It's the same. It's the auf Deutsch Richtungsableitung in the direction of n. That's exactly what I mean here. And if we would have a more general operator with some matrix, say k here, that would exactly the same thing if we would have used here correspondingly not the normal but the conormal derivative with a k here in front of the whole thing. That has nothing to do with the Laplacian, that here we get apparently this thing. So we need a compatibility conditions, necessary compatibility condition between the data. Saying, of course, what the source produces in total has to be, again, balanced by what the influx produces. And in fact, under this condition, there is a solution. The solutions can vary by a constant, and the constants can be fixed, for example, and it will be fixed in the situation when the solution appears as a stationary solution of a time-dependent process. Then the initial mass or energy of the initial data will, so to speak, fix the solution in the sense that because of this fixed flux condition, we will then preserve this quantity of the initial data. Okay, so this is the continuous situation now. That's to the finite difference method. We have discussed this already with central quotients, with central difference quotients and the ghost points in the way I have discussed it, in the way it now appears in this programming exercise. Okay, so what do we get then? Then we get a set of equations. This leads us to a set of equations, AH. The special thing of this matrix is now that all row entries add up to 0. It's because nothing in the star, so to speak, is lost. We have no Dirichlet boundary conditions. This means this is not a regular matrix, because the constant E, the 1 vector, where do I have it? The constant 1 vector, this guy here, is then in the kernel of the matrix. And we get a solution. So we get a system of equations which basically looks like that. I will not really formulate it out. So we have here something which has basically comes from our f evaluation of our f, and then let's write it in this form. We have something which has the form 1 over k, 1 over h, and then terms of the boundary conditions appear. That means these are those indices which are involved for the corresponding index we are looking at here. If we are in the interior, nothing happens. If we are close to the boundary and we come into a situation where we have to work with the discretization of the boundary condition, then of course these j values will come in, and this is meant here. And then here a factor 1 over h appears. This you should believe or check it. Or you will have to check this for your implementation. Now, what about the solubility of this set of equations? So we said already, this is a singular matrix. It has at least the constant 1 in the kernel. What can we say about the solvability of this set of equations? What do you know about it? Okay, to facilitate the situation a little bit, let me first assume something which we have not yet shown, namely, so what we have seen is that the vector constant 1 is in the kernel of the matrix, and let's assume that in fact we have not yet seen a proof for that in fact the kernel is just one-dimensional. It's just the span of this vector. So, and what we further know is AH is a symmetric matrix. Now we know everything really to characterize when this set of linear equations is solvable. That is my assertion. Let's call this star here. And let's call this right-hand side the shorthand writing. What kind of give me a letter, F, G, whatever, B. So what's okay? The first thing I think everybody of you can say: when is a set of equations solvable? What does the right-hand side has to fulfill? That's very, very trivial now. Don't be ashamed to say it. What about this? Right-hand side must be in the image of the mapping, isn't it? Okay, doesn't help us too much at the moment. Okay. I said the matrix is symmetric, so it's also in the image of the transpose. And now you have to know the only thing what you have to remember from linear algebra. The only statement which is of importance, from which you can derive all the other relevant statements. And what do I mean? What is this here? What is the magic equality? Never heard of this? Never heard of the four magic spaces connected with a set of equations? This is, of course, the image. This is the kernel. And what else? So we have the row space. This is, the column space. This is this. We have the row space. What is this? The row space expressed with the matrix is what? So the space generated by the rows of the matrix, not by the columns. It's the image of AH transpose, and then with the kernel of AH transpose. So how do these things are connected? You cannot tell me that you don't know that. This is the kernel of A transpose. The orthogonal is the orthogonal complement of the kernel of A. That's all. This identity is all what you have to know from linear algebra. Forget the rest. Because everything you can derive from this identity. Okay, what does that mean? If we take this into account here, this knowledge here. What does it mean? Solvable exactly if the right-hand side is orthogonal to the kernel of A. Orthogonal to the one basis vector. Orthogonal in the Euclidean scalar product. Orthogonal to the identity 1 vector. What does that mean? I have to be able to add up all the quantities on the right-hand side and have to get a 0. That means I have to sum over the f values, and I have to sum over all over the g values, and I get a 0. That is the requirement. Okay? Or maybe we write it in this form. Looks a little bit nicer. Why does that look nicer? Do you see now the correspondence? This is this, and this is this here. Okay, so maybe it's sometimes linear algebra is quite useful. Okay, so now we stop with finite differences and come to finite elements. What are finite elements? This is a very popular, very often used in the last 30, 40, 50 years, since the 1940s. Used in the event of the computers, then used method in engineering to compute approximate solution of partial differential equations. It started in aerospace industry, then went over to fluid mechanics, heat conduction, mathematics produced all the theory. So this is a very well-developed subject nowadays. Originally, it was already formulated in the 20s in American mathematics, but of course, this was the time where no computers exist, and so one could not really do too much with it. It combines various old and new ideas. The old ideas are goes by the name Galerkin method. That was a Russian mathematician. And Ritz method, and we will see in this very simple example, which corresponds to our Poisson equation, these things then coincide. So one also then says Ritz-Galerkin approximation sometimes. And this is something very old. Galerkin did this already at the end of the 19th century, and he did some hand computations. And then a new idea was added to that, and we will then see what this new idea is. But really, to apply this for partial differential equations, we need a new point of view to the partial differential equations. We need a new formulation. And we have seen already that this pointwise view of this pointwise notion of solution has its problems. We not really know, or only know it in a few examples. What to do if, for example, our coefficients, which are inside of the divergence, for example, are jumping functions. Then, of course, we cannot say differentiate everything out, and these are then the terms in our equations. So we need a notion of solution which is a little bit weaker. And I said already in the beginning, in principle, we are allowed to put down every notion of solution we would like. The only thing what should not happen is that we lose uniqueness. So we are allowed to weaken the notion of solution, but only to the expense not to lose uniqueness. And the other thing is with the boundary condition, how to bring in the boundary condition into the problem. And there we will see there's a big distinction between Dirichlet and Neumann boundary condition or flux boundary conditions. Up to now, we had the impression, yeah, Dirichlet is good. It's maybe a little bit problematic with this general boundary for a general domain, but in such a case, we could not deal with flux boundary conditions. Much easier to deal with than with flux boundary conditions. This point of view will turn around completely. We will see that actually the flux boundary conditions are the natural one, and the Dirichlet boundary conditions are the violent, the imposed ones. Okay, so what do we do? So the first part now, this is semi-formal or semi-rigorous in the sense that I have tried to develop also, so to speak, a little bit for a non-mathematical audience to develop a very inductive approach to this. So of course, everything can be made rigorous, but then it doesn't make sense to go this inductive way. Then I could have started immediately with the exact formulation. So you have to see it a little bit under this point of view. So what we do is, first of all, we need a new basis space, and we enlarge the space. We do not use the continuous functions anymore, but our basis space is now the L2 of omega. These are these functions where the square of the function is integrable. And integrable always means in the sense of Lebesgue. And the mathematics students, I hope they know what that means, and the engineering students, they have to, believe what I'm saying. I cannot explain now what it is. So, okay, but you have some idea what an integral is, and this will help us, I think. Okay, on the L2 space is a space with a scalar product. This is written down here. So we only have real valued spaces at the moment, or all the time. And I indicate the scalar product with a bracket with a 0. And correspondingly, the norm, which is induced from the scalar product with the norm with index 0. That is the notion which I've used already. And the 0 refers to the number of derivatives which appear, so to speak, here in the definition. And apparently we have no derivatives here, therefore a 0, and not a 2. A 2 would be misleading in this sense. Okay, so this is a scalar product on this space, meaning this is linear, bilinear, linear in each component, it's symmetric, and it's definite. And of course, the L2 property makes it well defined. This is also, we have then the relation between scalar product and norms by the Cauchy-Schwarz inequality. These are things I will now use quite often. To be very precise, you will know that to get this definiteness, we have also to give up a little bit this pointwise notion of a function, because we can change a function on a set of measure 0 without changing the integral. That means if we say really think naively of functions, we don't have definiteness. We cannot conclude from saying the integral of u squared dx is 0, we cannot conclude u is equal to 0. We can only conclude u is 0 on a set, up to a set of measure 0. So actually we have to deal with equivalence classes of functions in the sense that we can change a function on a set of measure 0 without changing the function. That's how we will do this all the time. Okay, that is what I just discussed. So we have to take into account that if we change a function on a set of only on a set of measure 0, it's the same function. So if we speak about the 0 function, it always means 0 up to a set of measure 0. That also means if we say a function f from L2 is a continuous function, that of course means it has a continuous representative. If we were too stupid not to choose them, we could even have ended up with a representative which is then not continuous on a set of measure 0. Okay, and of course sets of measure 0 can be pretty big, as we know. For example, this function here, which looks a little bit, looks very non-zero, is a function which is 1 on the irrational numbers, and it's 0 on the rational numbers. It's a continuous function, namely it's a continuous function 1, in this sense I have just described it. The rational numbers do not play a role. Okay, so the other ingredients what we use, and of course this requires certain smoothness assumptions on the domain we are using, is the validity of the divergence theorem, of the integral theorem of Gauss, which we have used already several times, saying I have a vector field with certain regularity properties. I have the volume integral of the divergence. I can express this as the surface integral of the normal component. Okay, so let's start again with our model problem, and we make it even easier in the sense that we only consider first only homogeneous Dirichlet data, u equals 0 on the boundary. Okay, so as I said, we assume our domain is such that we assume everything what I'm doing is allowed. So this is only semi-rigorous what I'm doing, and I start with a classical solution of this problem. And really to make sure that what I'm doing is allowed, I have even to assume that the solution is not only continuous up to the boundary, it's even C1 up to the boundary. We have seen that even in the case of a rectangle, this is critical. But let's assume this for a moment. As I said, that's only a formal introduction to the whole thing. So the idea is now not to look at the equations furthermore in a pointwise sense, but only in an integral sense. So in we are taking now, say, a measuring device, which is not able really to resolve one point, but it can resolve as close as possible near to one point. It can resolve at every point. So we have all kinds of measuring devices. And here this is described by the concept of test functions, Testfunktionen. And for this, for a moment, we use functions which are C infinity. That means infinitely often continuously differentiable. And the 0 here indicates they have compact support. So maybe you don't know what the support of a function is. The support of a function f, say f defined in Rn, I take those points at which the function is non-equal to 0, and from this set I take the closure. That is the support of the function. And having compact support means this set is compactly embedded in the domain, and the domain is always open. So the situation is, this is our domain omega without the boundary, and the compact, this is always a closed set, and this then necessarily mean the boundaries of this set have to stay away from the boundary of the domain. So this then maybe is the support of f. That means f might look like that here. And because of the C infinity property means all derivatives are 0 at those points here. What's not allowed is what is not this is C 0 infinity. So this here could be a C infinity function, but it's not in C 0 infinity. Having a test function, this is like not sure whether I'm allowed to say this. If you do your housework and you're not very fond in doing your housework, then you always stay away from the corners doing dust cleaning. That is something like that here. That means the boundary cannot do us any harm in all our calculations. So this are the test functions. What we do with the test functions, we multiply the whole equation with a test function, with an arbitrary test function, and say these infinite amount of new equations which we now get are those equations which we want have to be fulfilled. So first we had our infinite degrees of freedoms in the first case where all those points where we had the requirements. Now the infiniteness of the problems comes from the infinite amount, from the infinite dimensionality of the test space, which produces us now an infinite amount of equations in some sense. So what does that mean? So we multiply it, we start with the right-hand side. We multiply with the test function. So this is just the scalar product in L2. So we plug in here minus Laplacian in the form divergence of gradient. And as we can, I think you know this all, an immediate consequence of the divergence theorem is the formula of partial integration. So we can, so to speak, bring the divergence as a gradient to the v by change of a sign. And in addition, we get a boundary integral here. But this boundary integral here vanishes because of this compactly supported test functions. That means we have this identity here for a classical solution. And you see now such that this equation makes sense, we now only need one derivative and not two derivatives for function u with certain properties. So we now define this term which we got as a new bilinear form, AUV. So this is gradient of u times gradient of v in the integral of that. That's again bilinear as our L2 scalar product. It's symmetric. So at the moment it's defined, it's a little bit asymmetrically defined for our test functions and for the C1 omega bar functions. If we ignore this for a second, then we can say what we have seen is that a classical solution fulfills this equation here. AUV equals FV in the L2 scalar products for all test functions f from C infinity 0. This is what is called a variational equation. So it's an equation, and it's variational in the sense that we can vary the test functions here. It's not one equation, it's as many equations as we have degrees of freedom in the test functions. Now, let's look at this quantity A. First at the space of test functions, where in any case it's well defined. And the assertion is there it is not, it's a scalar product. So we said it's bilinear, it's symmetric. So what is still missing for a scalar product? What do I have to check for this claim? What is missing? Yeah?
It has to be definite.
The definiteness, exactly. So what does that mean? What we have to assure, we take u equals v, so we get here gradient of u modulus gradient of u squared. And we have to conclude from the fact that the integral of this function is 0, we have to conclude that the function is 0, in this sense of L2 function as I have described it. So the first argument is to see that the gradient of u is 0. And this is easy to argue because here we are really in a situation of continuous functions. So if gradient of u in Euclidean norm squared would be positive, it would be positive at a small area around this point. We could bound it from below by a positive number, then we could also bound the integral from below by a positive number. Opposite to the assumption that the integral is 0. Then the gradient of u is 0. And what does now tell us that also u is 0? In general, I can have very smooth functions where, for example, the function equal to 1, also the gradient of u is 0. What property in this space now plays a role? What further property? What do I need? Yeah? It's 0 on the boundary, the compact support, the compactness of the support. Okay, that gives us the definiteness in this case, and by that means we also now have a second scalar product defined by this others, a second norm defined by this other scalar product. This gets the index A. And if I work this out, what this is, it looks like the scalar product we had, the norm we had before, but now not the function appears, but the gradient of the function. Okay, so here it's exactly this argument which I've just given for the proof of the definiteness. So, what is now a little bit not so pleasant at the moment as we have a different space where the solution lives, the C1 omega bar, and the test function. And we would have to have those functions to be the same. But of course, we cannot take the test function as the space for the solutions because this would be much too small. We would be restricted to just a few problems where really the solutions has this property. So we now have to try to enlarge a little bit the space without doing harm to what we did till now. And this is a first attempt. It's not the final attempt and not the right attempt, but it's a first attempt in this inductive way to do this. So my first attempt is that I say, okay, I take functions which are continuous up to the boundary, and I want that the partial derivatives exist piecewise and are piecewise continuous. And what shall piecewise mean? It shall mean that I can subdivide the omega in a fixed finite set here, where maybe I have to do some further assumptions to really make this reasonable, but you will later on see what I have in mind with this. So maybe you can construct very strange subdivisions, but if you think of a reasonable subdivision, then you are right. So at each of these open sets, the function is the derivative exists, and it does not explode to the boundary, but it can be continuously extended to the boundary. That is the assumption. So functions which are in one dimension, functions which I have in mind, let's say this is omega, this is my subdivision, so let's say, so this would be, for example, a function which I would allow for. Okay. Because this is, so to speak, one space where I can do all these operations I've done till now. I can now do this, take the subdivision to the partial integration on each of the subdomains and put it together again. And this continuity ensures that the internal boundary integrals which appear, they just cancel each other. Because what is the normal from the one hand side is minus the normal from the other side. Okay, so what do we have then? The first thing is, also in this enlarged space, this A is a scalar product. Symmetry, bilinearity is no problem, and definiteness we have to go through the proof, and you will see this proof goes over. Of course, this smaller, much smaller space of test functions is in this larger space. But what is now important, which I'm not going to prove, is that we have density. That means the space of test functions is dense in this larger space, in this space V, both with respect to the A norm and with respect to the L2 norm. What means density? It means I can find a sequence of functions which converges in the specified norm towards this norm. So how would I do this here? There are two problems here involved. Of course, let's first look maybe to the L2 norm. This is a little bit easier to comprehend. What is the problem here? I have three problems here in the approximation. Where do I have to do something here to approximate this with C infinity 0 functions? Where I have to which of these points I have to take care? Or is this, maybe this already a C infinity 0 function, and I don't have to do anything. Here I have a problem, and where else? The support is also not okay. So what I have to do is I have, so to speak, let's assume here in between it's C infinity, I have to do something like that, and this epsilon has to become smaller and smaller, such that the integral difference of the square goes to 0. And also here I have to do something in the sense that the integral difference goes to 0 in the square. And one has the impression that is possibly, we can possibly do that. Okay. We will later show a much more general assertion, therefore I do not do a proof of that. So, okay, so we have now, what do we have now? We have this A defined on this space V now. We have the test space dense. And now we are saying that now the first assertion is if I have a classical solution with this additional requirement continues up to the first derivatives up to the boundary, then this classical solution fulfills this variational inequality, but now with the test functions not from the C infinity 0 only, but from the full space V. And if this is really true, now I've gained what I want to have. On the one hand side, I have my solutions from the space V. On the other hand side, the test functions are from the space V. Let's see why this holds true. And this is due to the density of this smaller space. So because of the density, yeah, there's one thing missing. We have to assume here, maybe you add this, we have to assume a set is a semi-form, a semi-irregulars here, everything up to a certain point. We have to add here that the F, the right-hand side, is in L2. You will see this in a second where we need this. So how do we argue? We know the density of the smooth test functions in the A norm. So we have a sequence, and in the 0 norm, and if we choose a sequence and again a subsequence, we can finally end up with a sequence which converges both in the L2 norm and in the A norm. So what does that mean? That means that we have this left-hand side of equalities, because this was our derivation of the variational equation with the smooth test functions, with the Vn. Now the Vn converges to V because of in L2. But what we have here with the scalar product is a continuous functional on L2, and therefore the whole thing converges here too. For this we need that the f is an L2 function. Due to the same thing holds here true, holds here also a scalar product is continuous in each of its components with respect to the induced norm. This is basically the Cauchy-Schwarz inequality. And therefore, as Vn converges to V, also AuVn converges to AuV. And that means the sequences are the same, therefore the limits have to be the same. Therefore, we have the variational equation now for the general type of test functions, for the V from capital V. Okay, so far so good. And this gives a new name. We call an element from capital V a weak or a variational solution, schwache oder variationelle Lösung, if it fulfills the variational equation, die Variationsgleichung. This also has a corresponding physical interpretation in all those models which we a little bit have discussed. For example, if we think of the Laplacian or of the boundary value problem we are looking at as a model from mechanics describing the displacement of an elastic membrane which is clamped at the boundary, then this relation would be called the principle of virtual work. So this is something which is in some sense known in mechanics. So what we have shown up till now, a classical solution is a weak solution. The strategy will be, and later on we will formulate a framework which will give us all these results. Strategy will be to fix a framework where always a weak solution exists. And the aim, so to speak, of the finite element method is to approximate the weak solution. And by this, under further regularity assumptions which are not so severe as we have seen it with the finite difference method. And you've seen we need much more, we have much less requirements. We have less smoothness, we only have a first derivative, no second derivative, and we only need to have that the function is in L2 and the derivatives are in L2 up till now. So up till now I have missed something, and actually you should complain because I've missed something. Namely, I've missed the boundary conditions. We had two equations. We had the PDE and the boundary condition. And up till now, I only dealt with my manipulation of the equation. Of course, I only dealt with the PDE. So the boundary conditions are not yet in the problem. And that is typical for the sterically boundary conditions. And the only way I can do, now I have to go back to my definition of V. I skipped here something, namely I have to put the boundary conditions in the space V here. And this is also what I then also need to do this in the partial integration step to get rid of the boundary terms. So here with the requirement that all elements of this space V have to be 0 on the boundary. And at the moment, that has a clear meaning what it says, because I say it should be a continuous function up to the boundary. Then it says a clear pointwise meaning saying this function is 0 at the boundary. Later on, we will give up this formulation, and then we have the problem in giving this u equals 0 on the boundary a new sense. So the boundary condition is in the space. It helps us in the derivation of the weak formulation, and the weak formulation now substitutes the PDE. That's the situation. Okay, there's another type of formulation. Okay, let me put it in this way. If you have looked at sets of equations with symmetric positive matrices, you might have seen that those sets of equations are equivalent to a quadratic minimization problem. Rings a bell? No? At least those who have already looked a little bit in iterative methods for solving sets of linear equations, they should know that, because the gradient method, and in particular the conjugate gradient method, they are based on this equivalency. And actually there's also a physical meaning behind this equivalency, and we will see this because we will see something analogous here in this infinite dimensional case. The point is that the variational equation we have formulated is equivalent in the sense that it has the same solutions. We have not yet stated conditions under which solutions exist or are unique. There might be none, there might be several. It's equivalent in this sense to a minimization problem on this function space V. And the functional is the following functional: 1/2 times AVV. So this is, like, if you want, that's the A norm squared. So this is a quadratic term, V and V, minus a linear term, the L2 scalar product of the right-hand side F with the test function V. And this, in this mechanical application, this formulation is then called the principle of minimal potential energy. In the specific situation, this is nothing but the potential energy here. Let's have a look at, let's do this equivalency proof here. So we have to look at two directions. We have first to start with a solution of the variational equation, show it's a solution of the minimization problem, and vice versa. Let's start with the first direction. And okay, so what we want to do is so we have the solution U, and we want to compare the solution U with a general element V under the action of this functional F. And of course, we want to figure out that F of this general element is greater or equal than F of U. Then we have that the U is the global minimum, is a global minimum. Okay. To do this, we can write we define W as F minus U. Of course, then we have, W as V minus U. Then V is U plus W. So W is, so to speak, the direction in which we have to go to end up with a V. And plugging this in here into our functional, we see we have a quadratic term, and we have the linear term, and now we just multiply everything out, as you have done this already quite often with bilinear terms and with linear terms. And so what do we get? So we get the UU term, we get the WW term, then we get a UW in the UW term. They go together because of symmetry. That's this term, therefore we have a factor 1 in front of that, and these are the two terms from the linears. And what do we see? We have those contributions which come together for the F of U. Then we have this term here, 1/2 AWW. And what is then still left is this AUW minus FW. Why I have omitted this here? Why I have omitted AUW minus FW? But that's the variational equation for the test function W. The nice thing is with the variational equations, we are free when we say we have a variational solution, we have a weak solution. We are free in choosing the test function and to explore what that means to be a variational equation. And that is what we're doing here. We have our solution U, we have our, so to speak, comparison element V, and on the basis of that we compare a very special test element which helps us then here. Okay, the only thing what we still need to know is that this quantity is greater or equal to 0. That is a less strict requirement, then positive definiteness, and then we have the conclusion. And you see, if this is a very general proof, and it only needs the symmetry of the A, and it needs the positiveness in the sense that A WW is greater or equal to 0. It does not need the definiteness. Other direction? So we have a minimum, and we want to conclude that it's a solution of the variational equation. So what does that mean? Minimum, so this V is a very large space. It's an infinite dimensional space. Actually, in the sense of linear algebra, it has uncountably many. Usually in this, what I've picked down in the other real correct spaces, they have uncountably, the dimension is uncountably infinite. So that's very, very large. But of course, if we have a minimum of such a large space, we have a minimum also in each direction which we choose in this space. There are many directions we can choose, so we choose one. We take a V, a direction, so this is, do a little bit affine geometry if you want, in infinite spaces, and we go in this direction. So we have now a straight line defined by the point U and by the vector V, U epsilon V. This gives us now a function in the real parameter epsilon. And what do we know? We know, of course, that U plus epsilon V is greater or equal to F of U, because this is always smaller for every comparison element here. That means this new function G has a minimum in the point 0. So if this function G would be differentiable, then we would know what to conclude then, having a minimum. Okay, is this G differentiable? So we work out what this G is. So we plug in again this U plus epsilon V. It's the same computation as before. Now, I think before this V was called W, and now there's an epsilon in front of that. And correspondingly, how often the V appears, an epsilon goes out. And so we get terms without epsilon. We get terms with one epsilon, and one term with epsilon squared. So what we see here, in epsilon, U and V are fixed quantities. In epsilon, it's just a parabola. So we don't have to care about differentiability. So this is just a parabola which is open from above, because the UVV is positive. It's good that it's open from above. Otherwise, we would have a little bit of problems with the minimum. Okay, so what does that mean? The necessary condition for a minimum, that's the derivative at 0 vanishes. But what is the derivative of 0? It is just this quantity here. And this quantity being so 0 means the variational equation is fulfilled for the test function V. And V was a general chosen test function. So we have the variational equation. And as I said, if we look at this proof again, we see we can do this in a general vector space as long as A is symmetric and positive bilinear form. The right-hand side should be linear. So it's not necessary that it's of this form scalar product FV. It can be just a linear form. And yeah, that's all. So we have now two formulations which turned out to be equivalent under these conditions. The one is the variational equation, Variationsgleichung, and the other is the quadratic minimization problem. Okay, so we have put down a notion of weak solution, and I said the most important thing what we have to check is that the solution is unique. So we don't know conditions till now which guarantee us that a solution exists, but let us check at least that the solution is unique. And that is very easy to do. Assume that we have two weak solutions, U1 and U2. So both fulfill this set of these equations. So we subtract this equation, and the difference now fulfills also, if you want, a variational equation, but now with the right-hand side 0, because the right-hand sides have cancelled by subtracting these two lines. Okay, and now we are still free to choose the test function. And now, of course, now I'm allowed to choose as test function U1 minus U2. then I see that A, U1 minus U2, U1 minus U2 is equal to 0. And if I now know that the bilinear form, that the A is definite, this can only work if this vector is the 0 vector. So assuming that, knowing that the A is definite means U1 is equal to U2. And again, if we want to put this in a general framework, we only need here, I think this is written down here, this is valid in general, if A is a definite, so now we need definite bilinear form and B is any linear form. Okay, so up till now we have worked with, we have one space, the space V, which is not yet correctly defined, and we have two norms on this space, the L2 norm and this new with the function squared in the integral, and this new A norm with the gradient squared in the integral. Is it necessary to deal with these two different norms, or are they not more or less the same? We discussed this already a little bit and remembered that in an Rn, in a tuple space, in a finite dimensional space with fixed dimension, all norms are equivalent. But this need not to be true, or generally is not true in an infinite dimensional space, and it's also not enough to know, we saw this already with the finite difference method, if we look at finite dimensional spaces, but we look at a whole family of finite dimensional spaces with increasing dimension. And the same situation appears here. Those two norms are they compare to each other, but they are not equivalent. So equivalency would mean if I have convergence in the one norm, I have convergence in the other, and vice versa. So that would, changing the norm would only mean changing the number in weighting the difference, but would not change anything what is related to convergence, Cauchy sequence, openness, closedness of a set whatsoever, everything what's related to topology. The other situation is the situation what we have here, that one norm is stronger than the other, but not vice versa. That means if we have convergence in one norm, in the stronger norm, we also have convergence in the other norm, but not vice versa. And you know this already from the comparison of the L infinity norm and the L2 norm. You know that if you have convergence of a sequence of functions in the L infinity norm, uniform convergence, gleichmäßige Konvergenz, you not necessarily have vice versa. If you have convergence in the L2 norm, you not necessarily have convergence in the L infinity norm. And a similar thing we will now see here. Let's look at this sequence of functions. It's just a constant 1. And a small interval of length 1 over n here, I just connect this 1 in a piecewise linear fashion with 0 to fulfill my boundary conditions, to stay within my space. So this is a typical function in my space. So this is, here the derivative is piecewise existing and continuous, but it's not a C1 function, obviously. Okay. So here's the formula for this function, and now we can do things. We can compute the L2 norm, and if I want to estimate the L2 norm from above, I can do this very easily. I can more or less ignore these small things here, and I can estimate the L2 norm by 1 from above. So this is this estimate here. Now we come to the A norm. We are now in one dimension. The A norm is just derivative, the bilinear form is just derivative times derivative, and correspondingly the norm. And so if we now compute the A norm, from this middle interval we get no contribution. And here we have, as derivative, we have 1 over n. And here we have minus 1 over n. So we take the square of the modulus. So we get n square in both of the subintervals, and if we add this up, we get here square root of 2 times n. So here we have a bounded sequence, and here we have a sequence going to infinity. That means it's impossible to find a constant such that I can estimate from above the A norm by constant times the 0 norms. That means I cannot conclude from convergence in the L2 norm that I have convergence in the A norm. But the conclusion in the other direction, this is valid, and this we will prove later on. In this sense, the A norm is a stronger norm, a strictly stronger norm than the L2 norm. Okay, this is what I said. There is this estimate, and we will show this estimate a little bit later. That is then in this context called the Poincaré, or is related to the so-called Poincaré inequality. So we cannot yet be satisfied with the space what we have. And the reason for that is, of course, we want to have a setting where we can also be sure that a solution exists. But to have this situation, we not only need to have a vector space with a normed vector space as our basis space, we need to have a vector space which is complete, which is vollständiger normierter Raum, or what is called a Banach space, Banach-Raum. And to have this completeness, this definition we have up till now, this is not okay. And this you can see at this example, and with this I will close, then do the following. Look at this function here. So this is a linear function multiplied with a power, and the power is strictly between 1/2 and 1. So the square of this power is still integrable, but you see that the derivative develops a singularity. The derivative behaves like x to the alpha minus 1 at 0. That means it cannot be continuously prolongated to the boundary. That means this function is not in the space as we have defined it. There's the regularity of the derivative missing at x equal to 0. If I now smooth the function in a similar sense as I've done it before, so I take this function, I take the small interval with the length 1 over n at both ends, and here I just prolongate the function exactly in the same linear fashion. Then I can see, I do not do this computation now, that this sequence of functions we have shown is a Cauchy sequence in the A norm. But nevertheless, there cannot be a function which, this is now a little bit vague argument, there cannot be a function in the space V towards which this sequence of function converges, because this function, if it exists, must be this function. But this function is only in a larger space. So the space is too small in some sense. We've done what we could with this pointwise notion of differentiability. We tried already with the subdivision and piecewise and whatsoever, but it's not good enough. What does that mean? We need a new notion of derivative. And this we will then develop the next time.